Good morning. Here yet again for another lovely session of CENG 3325 Structural Analysis. This is going to be the 14th lecture in the video series, and today we're going to be continuing on looking at how to solve for the deflection in beams via integration. And in particular, I'd like to look at doing this via an example. So let's look at the tools that we have. Let's first consider this. So let's look at the tools in our toolkit. Mathematical tools in our mathematical toolkit. It's probably some sort of four-dimensional hyperbag or something. So we have our relation between shear, moment, and deflection that we've seen previously. So v of x is equal to the negative integral of w of x dx. We know that m is a function of x is equal to the integral of shear is a function of x dx. We know that the slope of a beam, theta is a function of x, is equal to the integral of m of x over ei dx. And we know that y is a function of x is equal to the double integral of m of x over ei both with respect to x, which is also equal to dx, which is also equal to simply the integral of the slope as a function of x, dx. So this is just as a review. These are the tools that we're going to use as we work through the following example. So let us work through this example here. Let us consider this example. So we have this. And we have ends A and B. And we have a load, 50 kips. We have a 50 kip point load at the end. Then the total distance, the total length of this beam is going to be 10 feet. So basically it's a fairly simple beam, which means the integration will be not too bad for this example, though you can imagine this can get very hairy fairly quickly. So we have a 10-foot long cantilever beam with a point load at the end that's going to put this into positive bending, which is unusual for cantilevered beams. And we're neglecting the self-weight of the beam. And so the reactions on this thing, we're going to have an AX, which will be equal to 0. But that we can solve for that, but that's fairly straightforward. We're going to have MA and AY. And these reactions should be hopefully fairly trivial to get. And AY here. So solutions. Or solution. So a sum of moments about A. Well, first step I should say is to get the reactions. And you know what? I think I might just give these to us because that should be fairly straightforward. One, get the reactions. This is elementary statics, and it's a very simple one at that. So MA is going to be equal to 500 kip feet clockwise. And then by a sum of forces in the vertical direction, we can get that AY is equal to 50 kips downward. And also that AX is equal to 0. There are no horizontal forces on the beam, so AX logically has to be equal to 0. Fairly straightforward. Next, I need to get the shear and moment functions. Although, actually, let me just go ahead and get the shear and moment diagram, and then we can just get the shear and moment functions from that. Or we can do it two ways. We can either do it by inspection or by integration. I think for this, I'll just do it both. Why not? Show both ways. So two V and M diagrams, get your shear moment diagrams. So if you have your shear in kips, let's say we have our shear in kips, and we have our moment in kip feet. Well, by inspection, I can say, because there are no distributed loads, that first the downward load at the left end of the beam is going to cause shear to drop down to -50, and it's just going to remain constant all the way across the length of the beam. And then the end load will cause it to jump back up to 0. Now, so we have negative shear all the way across. Then I also know that the area under this is going to be -50 times 10. So the whole thing will drop by 50 as we go along. But the end load on the left end of the beam, or the reaction, is going to cause the moment to jump up to +500. And then it's going to linearly drop down to 0, because the area under this is -50. And so it'll drop down to 0 at the end. And this will be in positive bending. Okay. And we could get our shear and moment functions this way if we wished. I mean, these are pretty easy functions at this point. We could just say V as a function of x is equal to -50 kips. Or we could say that m, and then we could say that m as a function of x is equal to 500 minus 50x. So that would be one way to get our shear and moment functions very easily. Okay, and I should probably put a 500 on there. And then let's instead look at getting our shear and moment functions via integration. So I could do that as well. And if I wanted to do that, I would say that v of x is equal to the negative integral of w of x dx, which is equal to 0 plus, well, it's equal to the integral of -0, or the negative integral of 0 dx, and that's going to be equal to 0 plus c1. And boundary condition on this, as we saw previously when working through shear and moment functions by integration, we always need a boundary condition. And here, we always know that we're going to have we do know the shear at the end of the beam, and the boundary condition is that V at x equals 0 is equal to -50 kips from the reaction. And so therefore, C1 clearly equals -50, so V as a function of x is equal to -50 kips. Then I can apply my relationship that m as a function of x is equal to the integral of V of x dx. And I can integrate this. And that's going to be, let's see, that's going to be -50x plus c2. -50x plus c2. And my boundary condition, I could do two different ones. Two different ones are possible. I could say m at x equals 0 equals 500 kip feet. This one will be easier. Or I could also say that m at x equals 10 feet is equal to 0. Well, actually, either one. It's hard to tell which would be which would be easier. So I'm just going to go ahead and use the 10 because that'll actually equal 0, so that'll be kind of nice. So I'm going to use this one. -50, basically the moment at the free end must be 0 unless there is unless there is a couple at the end of it. So -50 times 10 plus C2 is equal to 0, which leads us to that C2 is equal to 500 kip feet. And therefore, m as a function of x is equal to -50x plus 500. And that's the same thing as we got before. Same thing as we got before. So next, I'm going to move on to finding, say, the slope as a function of x. So theta as a function of x, as we learned previously, is equal to m over ei, or m of x, over ei dx. Or I could also pull out the 1 over ei, and that will be just the integral of m of x dx. So this is then equal to 1 over ei, our same 1 over ei, that's our constant, times, well, not the integral, sorry, that will be times negative 25x squared plus 500x plus c3, plus 500x c3. Okay, so we need some boundary conditions. So I'd like to take a bit of a break here and talk about boundary conditions for deflection and for curvature. So this is negative 25x squared plus 500x plus c3. Okay, so possible boundary conditions. For a pin or roller connection, pin or roller, basically wherever you have a pin or roller, y is equal to 0. So if you have a pin or a roller or a pin, at this point, for both of these, y is equal to 0. The deflection is equal to 0 at those points, because that is the definition of a pin support. It will be free to rotate, but it's not free to translate up or down. So if you have a roller support or a pin support at that location, y as a function of x must equal 0. Then if you have a fixed support though, well, by definition, it is a fixed support. It is a fixed support by definition. So at that location, neither curvature nor deflection can be non-zero. So if you have a single fixed deflection, or sorry, a single fixed support at this location, theta equals 0 and y is equal to 0. Both theta and y are equal to 0. Theta and y are equal to 0. So these are some important boundary conditions to know. And these will really be our tools for solving these higher order integrations. So here, our boundary condition, for this case, we can simply use the relationship or the knowledge that theta at 0 or theta at x equals 0 is equal to 0. It is a fixed support, so the rotation there, or the slope, must be equal to 0. So then if I do that, if I plug that in, I can clearly see that C3 is equal to 0, so therefore theta as a function of x is equal to 1 over ei times negative 25x squared plus 500x. Plus 500x. And next, I want to develop the final equation, which will be the deflection equation. So 5, develop y as a function of x. And we know that y as a function of x is equal to the integral of theta as a function of x dx. And this is going to be equal to 1 over ei times, let's see, well, that's going to give us, well, just substitute, I should probably do that right now, times negative 25x squared plus 500x dx. My x's look like lambdas. And so then that will produce a 1 over ei of negative 25 over 3 x to the third plus 250 x squared plus c4. Plus c4. So boundary condition. Now we do need a boundary condition, and because this is a fixed support, we can simply say that y at x equals 0 is equal to 0. And so then 0 equals 1 over EI times negative 25 over 3 x, well, times 0 cubed plus 250 times 0 squared plus C4, which leads us to that C4 is equal to 0. And so, therefore, I can get my final y as a function of x equation. Y as a function of x is equal to 1 over EI times negative 25 over 3 x to the third plus 250 x squared plus 250 x squared. And that would be a final y as a function of x equation. So if I want to get, for example, if I wanted to apply this, if I wanted to ask the final, let's say I asked, what is the max deflection? If I ask the max deflection, well, it's clearly going to be at the free end of the beam or at max deflection or max y of x at x equals 10, the end of the beam. So I can simply substitute that in. Y as a function, y at x equals 10 is going to equal 1 over EI times negative 25 over 3 times 10 to the third power plus 250 times 10 squared. And this will then equal, produce a final deflection of 16,667 divided by whatever EI are. Or divided by whatever the EI may be. We would have to actually know the E and I of the beam in order to get that. All right, questions on that? Yes?
What is slope and deflection measured in?
Okay, so what is slope and deflection measured in? Slope would be measured in more like radians per inch, and deflection would be measured in simply inches, or whatever unit you have. So actually, I would like to give a few notes on this. Comments. Common Pratts and pitfalls, things like that. One, watch your units. You have to watch out for your units. So, for example, here, I did this integration in kip feet. So this is like kip feet to the third power. I did this all in kip feet. So what you would have to do is, if you didn't want to do this in inches, if you didn't want to redo the integral or readjust it or convert or something, you would have to put E in as kips per foot squared instead of kips per inch squared. And you would have to convert that into feet to the fourth power instead of inches to the fourth power, which is something I'm more accustomed to. So if you're working through problems like this, what you often might do is, it would probably behoove you, if you really want to avoid doing a lot of conversion, what I probably should have done is I probably should just done the whole integration as 100 with a beam length of 120 inches instead of a beam length of 10 feet. So, you know what? That's kind of a foolproof method for this. If you want to do that, that's probably the simplest way to do it. Just when I need to work through a longer one by hand, that's what I'll do myself. I will just go and automatically convert the beam length into inches if I'm doing it in inches, or if I'm doing metric, I'll just automatically convert it to meters. Basically, convert it to whatever units your moment of inertia and your modulus elasticity already are in, and that way you can avoid a whole bunch of headaches with your units, because otherwise you are going to get some weird answers, and I can pretty much guarantee you that somebody on the exam coming up is going to have a unit error or two, but it happens. 2, you will need boundary conditions. And for a fixed beam, it's relatively simple because you have the deflection and the curvature being equal to 0 at one point. That's very convenient. The problem is with what about a simply supported beam? With a simply supported beam, there is no point where the curvature is equal to 0. Instead, you know that the deflection is equal to 0 here, and the deflection is equal to 0 here. So what you instead need to do is you need to work all the way through the deflection you work through the deflection with two, basically keeping a C3 and a C4. Then you substitute in those at the end when you have the final deflection, and you solve algebraically for C3 and C4. So what else? Other notes? As we've seen, theta is a function of x, and y is a function of x. Very similar to building, let's see, v and m functions. And finally, 4, watch for discontinuities. Always and always watch for discontinuities. So this beam here, we only had discontinuities at the beginning and end of the beam. For more complex beams, you will have things that aren't so simple. You'll have deflection, or you have discontinuities at locations throughout the beam. So, all right, any questions on this, the assumptions baked into this, the method therein, etc.? Okay, all right, that'll do it for this lecture. Thank you for watching, and as always, thank you.